Welcome back, everybody. Today we're going deep on something pretty wild. It's called discrete sequence filters, DSFs for short.
Yes, DSFs.
We're going to be working mostly from Damien Fascio's reference paper on the subject. And this one's a real head-scratcher.
Yes, yeah.
We're talking about a whole new way of thinking about computing, one that could even change how we think about artificial intelligence.
Absolutely.
Now, you might be thinking, why should I even care about some new type of computing?
Right.
Well, imagine a world where computers can learn with way less data, making them more efficient and potentially way more sustainable.
Yeah, that's the big draw.
That's the promise of DSFs, and that's what we're going to unpack today.
Yeah, the thing about DSFs is that they're designed to work in situations where there's not a lot of data. And they work on pretty simple principles, which makes them incredibly efficient. You can almost think of them as a counterpoint to the data-hungry AI we see everywhere today.
So, Damien Fascio, he describes DSFs as this computational logical system based on information representations which work with scarce data. Yeah. It almost sounds like a completely different language, from the ones and zeros we're used to.
You're right. It's not about number crunching in the way that we typically think about it. It's more about sifting through information.
Okay.
Extracting meaning, making decisions based on what it finds. It's almost like a very, very rudimentary AI operating in a data desert.
And to help us understand this, he uses this analogy of envelopes and papers, which I thought was super helpful to visualize how these DSFs actually work.
Yeah, it's a great way to understand the basic elements. So imagine you've got a bunch of envelopes.
Okay.
Some are empty.
Okay.
Some have blank paper inside. And others have paper with information written on it, like an X or a Y.
Oh.
And these elements, they're the building blocks of information in a DSF system.
So like an empty envelope would be just E, and then if it had a pink piece of paper, it would be E, and then IP with an X would be E.
Exactly. That's exactly it.
Okay, cool.
And then all these elements interact inside what Fascio calls a database. And this is where those DSF operators come in. Think of the database as the stage where all the action happens, where the elements come together and the operators determine how they interact and transform.
Okay, so let's talk about these operators. Fascio introduces a bunch of them. We've got EMP, ONL, ONR, RAN, STR, MA, REC, each with their own specific function.
Yeah.
It's a lot to keep track of. What are the key things to know about these operators?
All right, well, let's break it down. Some operators, like EMP, ONL, and ONR, are what Fascio calls trivial operators. And that's because they automatically they spring into action in very specific situations. For example, EMP activates only when the database is totally empty.
Oh, okay.
Or only has empty elements.
So they've got these like built-in triggers that tell them when to activate.
Exactly. It's like they're programmed to recognize specific data configurations and respond accordingly.
And then we have these, what he calls non-trivial operators, like RAN, STR, and MAJ. These seem to be where things get really interesting, where decisions are being made based on like strength or majority or even randomness.
Yeah, you got it. These non-trivial operators, that's the heart of the decision-making power of DSFs. Let's say we have APX and EY elements in the database. Now, the RAN operator, think of this like a randomizer steps in when both these elements have equal presence.
Hold on, presence. What does that mean? Is that just how many of each element are in the database?
Well, it's a little bit more nuanced than that. Presence considers both quantity and what's called strength. You can actually assign different strengths to those elements with information on them. So you could have fewer EPX elements compared to EPI, but if EPX has a higher assigned strength, it can still have equal presence.
So it's like giving certain information more weight in the decision-making process.
Yeah, exactly, like a weighted voting system.
Yeah.
So going back to our operators, RAN relies on chance, but STR goes for the element with the highest strength, and then MAJ, as you might guess, sides with the majority.
Gotcha. And then there's REC, the recent operator.
Right.
That one seems a bit different from the others.
Yeah, you're right. REC doesn't just activate automatically like the others. You choose to apply REC.
Okay.
When the order that the information came in matters. It's like saying, I want the latest information, and REC gives you just that.
All right, so we've got our elements, we've got our database, and we have this set of operators. How do they all work together to actually process information?
Well, think of it like a step-by-step process, like a recipe within a sequence. So elements flow through an input, get processed in the database by an operator, and then you get an output, and a remain, what's left over.
Okay.
So it's like a recipe with really specific ingredients and instructions.
Got it.
And what's cool is Fascio gives these great examples of sequences in action. And it's fascinating to see how different operators can lead to totally different results, even with the same starting elements.
Yeah, he's got a bunch of good sequence examples in there. It's pretty wild. And it makes me wonder what happens when you have elements that have, like, neutral or empty information, like just EAP-E. Do they play any role in the outcome?
Oh, they totally do. Even though they might seem insignificant, elements like ape that represents neutral information, they can actually influence the outcome, especially with operators like RAN. It's a reminder that even neutral information can have an impact on the final result.
It's like a really delicate balancing act where even the tiniest bit of information can tip the scales.
Exactly.
So we've talked about these operators working in their natural environments, but what happens if you try to force them to work on a database where they wouldn't normally activate?
Ooh, that's when things get a little crazy. Fascio calls this using operators by decision. And you actually can force certain operators, except for str and maj, to act on a database where they wouldn't typically be triggered.
I bet there's a catch.
Of course.
Okay.
If the operation leads to an error, the whole sequence just stops. It's a risk you take when you push these operators too far.
So it's like a high-stakes game where you can manipulate the system to get specific results. But if you make one wrong move, the whole thing falls apart.
It's a tightrope walk.
This is starting to sound a lot like how our computers work now.
Right.
And that brings us to the really exciting part, how DSFs can actually emulate logic gates.
It's wild, isn't it?
It is. Logic gates, those are the fundamental building blocks of traditional computers. And the fact that we can mimic their behavior using DSFs opens up a whole world of possibilities.
It really does.
So how do we even begin to translate logic gates into the language of DSFs?
Well, Fascio gives us a pretty clever setup for this. Imagine a database that's preloaded with data and elements representing binary 0 and 1, the language of computers. Then, depending on the logic gate you want to emulate, you apply a carefully chosen sequence of operators to that database.
So Fascio walks through how to emulate a bunch of logic gates. Yes, not, and, D, or, NAND, NOR, XOR, XOR.
The whole gang's here.
I'm kind of curious, can we dive into a specific example?
Sure. Which one are you thinking of?
Let's take the NOT gate.
Okay, good choice.
It's like a fundamental gate that just flips the input. If you put in a 0, you get a 1, and vice versa.
Right, a classic.
So to recreate this with DSFs, you would preload the database with both APE representing 0 and EPIs representing 1. And then depending on the input, either EP for 0 or APX for 1, you apply a specific sequence of operators.
Exactly. And what's amazing is the output from that DSF sequence perfectly matches the truth table for the NOT gate.
It's like the DSF sequence is reenacting the function of the NOT T, just using its own unique language and rules.
It's a new way of speaking the same language, in a way.
Yeah, exactly. Can we look at another one?
Sure.
Let's try the A and D gate.
Okay, the A and D gate, it only outputs a 1 when both inputs are 1. Otherwise, it's a 0. Now, in the DSF version, a preloaded EP element makes sure there's a 0 output if at least one input is 0, because the MAJ operator, the one that chooses the majority, will pick EP, which again represents 0. The output only becomes EPX, which is 1 when both inputs are EPX, perfectly mirroring how an A and D GRE works.
Wow. So these really simple sequences can capture the essence of these complex logic gates. I have a feeling this is just the tip of the iceberg.
Yeah, I think so too.
Fascio even mentions some more advanced concepts like two-dimensional sequences and feedback mechanisms.
It gets pretty wild.
What can you tell us about those?
Well, with two-dimensional sequences, think about having multiple sequences all working together, like different parts of a brain. And then with feedback mechanisms, that introduces a dynamic element where outputs can actually be fed back in as inputs, creating loops. It's like, imagine the possibilities when you start combining these ideas.
Yeah, sounds like we could be at the start of something really revolutionary. But before we jump into all that, let's take a step back and reflect on what we've learned so far. This is pretty amazing stuff. What's standing out to you as the most important thing about DSFs?
I think it's the potential for a more sustainable, more efficient way of doing computing. In a world where we rely so much on AI, and AI needs so much data, the idea that there might be another way is really, really exciting.
Yeah, I completely agree. And this concept of DSFs being more like how humans think, that's got me really intrigued. But I have to admit, I'm still trying to grasp how these sequences of elements and operators can achieve such complexity.
Yeah, it's a lot to wrap your head around. Remember those advanced concepts we talked about, two-dimensional sequences and feedback mechanisms?
Yeah.
Those are really key to understanding how DSFs handle more complex stuff.
Okay, so can you give us an example of how those might work in practice?
Sure. Let's say you're trying to process information from a bunch of different sources all at the same time. Like, imagine a self-driving car. It's got cameras, radar, LiDAR, all that stuff.
Yeah.
And it needs to make split-second decisions based on what's happening around it.
Right.
That's where two-dimensional sequences come in. Instead of just one sequence, you have multiple sequences running in parallel, all interacting and sharing information.
So it's like weaving together multiple threads of thought to create a richer understanding.
Precisely. And then feedback mechanisms, those add a whole other layer of complexity. It's not just a one-way flow of information. It's a dynamic, interactive process.
So it's like the output of one sequence can actually be fed back into another sequence as input?
Exactly. And that allows the system to adapt and evolve over time, much like how our brains learn from new information.
So it's a much more dynamic and interactive process.
Yeah, it's really pretty fascinating.
And what are some of the potential applications of these advanced DSF techniques? It seems like the possibilities are pretty vast.
Oh, absolutely. We've talked about self-driving cars, but you can imagine applications in all sorts of fields. Robotics, where machines need to learn and adapt in real time. Modeling complex systems like financial markets or climate patterns. Even medicine. The potential is really huge.
And Fascio suggests that DSFs could even be the key to creating a Turing-complete system.
That's right.
That's a pretty bold claim.
It is. Turing completeness means a system can do any computation a regular computer can.
Right.
And considering DSFs can already do logic gates, it's not that crazy to think they could become Turing complete.
Yeah. So that would be like a monumental achievement, wouldn't it?
It would. It would mean that DSFs have the potential to not just change our computers, but to become the basis for a totally new kind of computing.
And who knows what kind of breakthroughs we could make with that.
The mind boggles.
It's really mind-blowing. But let's shift gears a bit and talk about some of the practical stuff.
Okay.
You mentioned the possibility of more sustainable AI. How much of an impact could that have on the world? Could DSFs help with some of the environmental challenges we face with our data-hungry computers?
That's a big question, and a lot of people are thinking about it. As we use more AI, data centers use more energy.
Yeah.
And that's not good.
Yeah.
But with DSFs being so efficient, they could be a solution. Imagine AI that learns with way less data. They could drastically cut energy use and have a much smaller environmental impact.
So DSFs could lead to more powerful and adaptable AI, and at the same time, help us make it more sustainable.
Yeah, I think so. It's all about finding ways to create a future where technology works with us and with our planet instead of against it.
It really feels like we're at the beginning of something huge.
I think so, too.
A completely new way of thinking about computation. One that's more in tune with how we humans think and more respectful of our planet.
It's a really exciting time to be thinking about these things.
So as we wrap up this part of our deep dive into DSFs, what's the one thing you want our listeners to take away from all of this?
The DSFs are a game changer. They challenge everything we thought we knew about how computers should work. DSFs show us that we can have incredibly powerful computation that's elegant and efficient and maybe even more human-like.
It's like we're witnessing the birth of a new kind of computational language, one that speaks to the complexity of our world, and maybe, just maybe, offers a glimpse into a future where technology is more aligned with us and our values.
A future where technology helps us solve problems without creating new ones.
A future worth striving for.
Absolutely.
And that brings us to the end of this part of our deep dive.
Right.
And in the next part, we're going to be talking more about the really mind-blowing stuff, like two-dimensional sequences and feedback mechanisms and all that.
Buckle up.
So stick around.
Welcome back. Before the break, we were talking about DSFs being potentially revolutionary. The more we look at these discrete sequence filters, the more it seems like we're looking at a whole new paradigm.
I'm really struck by this idea of DSFs as a way to create more human-like AI. You know, you were saying earlier how DSFs can work really well with limited data, kind of like how we humans learn. Can you talk more about that?
Sure. Think about how we learn as people. We don't need millions and millions of data points.
Yeah.
To be able to recognize patterns and make decisions. We can generalize, learn from just a few examples.
Yeah.
And DSFs, with their ability to work in these data-sparse environments, They seem to kind of mirror that aspect of human thinking.
So instead of making computers think like us by giving them tons and tons of data, could DSFs be a way to make computers that are just naturally more like us?
That's a fascinating thought. Of course, DSFs are still relatively new.
Right.
We're still figuring them out. But the fact that they make us rethink what a computer is and how it learns it is incredibly exciting.
It's like we're moving away from this idea that bigger is always better when it comes to computers.
Yeah.
And I have to admit, I'm still wrapping my head around how these simple sequences can do such complex things.
Well, that's where those advanced concepts come in. Two-dimensional sequences, feedback mechanisms, or we talked about those.
Yeah.
Those are really important for understanding how DSFs can handle more difficult computations.
Can you give us an example? How would those actually work?
Sure. Imagine you need to process information from a bunch of different sources at the same time. Like, picture a self-driving car.
Okay.
It's got cameras, radar, LiDAR.
Right.
It needs to make quick decisions based on all this information from surroundings.
Yeah.
That's where two-dimensional sequences come in. Instead of just one sequence, you have a bunch of them running at the same time, all interacting and sharing information.
So it's like different parts of a brain all working together.
Exactly.
Yeah.
And then feedback mechanisms, they add another layer of complexity because outputs can actually be fed back in as input,
Oh, wow.
creating loops and allowing the system to adapt and change over time.
So it's not just a straight line of information. It's more like a constant back and forth.
It's much more dynamic, yeah.
So where could we use these advanced DSF techniques? It seems like there are tons of possibilities.
Yeah, tons. We talked about self-driving cars, but you can imagine them being used in robotics where machines need to be able to learn on the fly, or modeling really complex systems like financial markets or even climate patterns.
And Fascio says that DSFs could even be the key to making a Turing-complete system.
He does, yeah.
Now, that's a pretty big deal, right?
It is. It means a system can do anything a normal computer can. And since we know DSS can already emulate logic gates, it's not impossible to think they could get there.
So that would mean DSFs could be more than just a new technology. They could be the start of a totally new kind of computer.
It's a pretty mind-blowing thought.
It really is. Well, let's get practical for a minute.
Sure.
We keep talking about more sustainable AI.
Yeah.
But how big of an impact could that actually have? Do you think DSS could really help us solve some of the environmental problems caused by our data-hungry computers?
Well, I think it's definitely something to consider. AI is everywhere, and that means more and more energy being used in data centers.
Yeah.
And that's a problem. But DSFs are incredibly efficient.
Right.
Imagine AI that can learn with way less data.
Huh.
We could see massive reductions in energy use, a smaller impact on the environment.
So we could have more powerful and adaptable AI that's also better for the planet.
I think so. It's all about finding the right balance, using technology in a way that benefits us without harming the world around us.
This really feels like the beginning of something huge.
I think so, too.
A whole new way of thinking about computing, more in line with how we humans learn and more sustainable for our planet.
It's a very exciting time to be working in this field.
So to wrap up this part of our deep dive on DSFs, what's the one key takeaway you'd like our listeners to remember?
I'd say it's that DSFs are a game changer. They make us rethink everything we thought we knew about computers. And they show us that amazing computation can be elegant, efficient, and maybe even a little bit more human.
It's like we're seeing a new computational language being born, one that can handle the complexity of our world and maybe even lead us to a future where technology works with us, not against us.
A future where technology is a force for good.
Absolutely. And that's the end of this part of our deep dive. But don't go anywhere. In the next part, we're going to be exploring some of the really mind-blowing stuff, like two-dimensional sequences, feedback mechanisms, all that good stuff.
It's going to be wild.
So stick around. You know, it's kind of wild to think this whole new way of computing could come from something as simple as envelopes and papers.
It is, yeah.
It really shows how powerful it is to just think outside the box. Sometimes the best ideas come from the most unexpected places.
That's true. It's a good reminder that we should always be challenging our assumptions and looking at things from different angles, like Damien Fascio did with DSFs.
So we've talked about DSFs changing AI and computing. But what about the ethics of it all? If we do end up with more powerful AI because of DSFs, what kind of ethical questions do we need to be thinking about?
Yeah, that's a really important question, and one we can't just ignore. Like with any powerful tech, we have to think about the risks and make sure these things are developed responsibly.
What are some of those ethical challenges that DSF-powered AI might bring up?
One thing is bias. Even though DSFs themselves might not be biased, the data we use to train them could be,
Right.
reflecting biases that already exist in society. And that could lead to AI systems that just make those biases worse. And that could lead to unfair outcomes.
So it's not just about the tech itself, but the data we feed it and the people who are building it, right?
Exactly.
Right.
It's so important to have diverse teams working on DSF-powered AI, to make sure different viewpoints and values are considered. We have to think about how these technologies could affect society.
So we need to build in ethical safeguards right from the start, not try to fix things later.
Exactly.
Yeah.
We need to think ahead. Think about potential problems and be ready to address them. It's not just about making AI that's powerful.
Yeah.
It's about making AI that's fair and just, beneficial to everyone.
Makes sense. It's a good reminder that technology isn't neutral. It reflects the values of the people who create it and the people who use it.
Absolutely. And with DSF-powered AI, it's so important to talk about these ethical issues. We need to make sure this technology is used in a way that helps everyone.
So as we keep exploring this new world of computing, we got to do it carefully, thinking about both the good and the bad.
For sure. It's about finding that balance, harnessing the power of DSFs while protecting our values and our future.
Well, this has been quite a journey. We started with envelopes and papers, and now we're talking about logic gates, two-dimensional sequences, and a whole new kind of computing. It's pretty mind-blowing.
It is, yeah. DSFs are a really elegant and innovative approach, and they're still so new. I can't wait to see where they go.
So, as we wrap up our deep dive into the world of DSFs, let's leave our listeners with this thought. What if DSFs are more than just a new tech? What if they're showing us a future where computing is more like how our brains work, more efficient and more sustainable, a future where technology serves humanity and our planet?
That's the dream.
A dream worth working for.
It is. And, maybe one day we'll look back and see this as the beginning of a whole new era of computing. And it all started with this idea of envelopes and papers.
Thanks for joining us on this deep dive into the world of DSFs. Until next time, keep exploring and keep those minds curious.